Okay, if you'll turn to page 8 in your book, we want to take a look at table 1.1, point out some of the important information there. Table 1.1 lists the common hydrocarbons that are involved in gas processing and some of their physical properties. The list on the left is the most common hydrocarbons. You'll recognize some of these names. Some of the names might be kind of strange to you. Methane, ethane, propane. There's two kinds of butane, isobutane and normal butane. You also have isopentane and normal pentane, hexane, heptane, octane, nonane, decane. The symbols next to them are very important. Y'all need to learn those. You need to learn C1 represents methane, C2 represents ethane, etc. Now, what does the C1 and C2 represent? C stands for carbon. Remember, hydrocarbon comes from the fact that oil field chemicals are made of hydrogen and carbon. The C stands for carbon, and the number next to it tells you how many carbon atoms are in that molecule. So what this tells you is there is one carbon atom in a methane molecule. Every methane molecule, an individual molecule of methane, has one carbon atom. Every individual molecule of ethane has two carbon atoms. Propane molecule has 3. Butane molecule has 4, and so on and so forth. And just to maybe help out with visualizing that, y'all might remember from your junior high or high school chemistry the way that molecules are arranged. A carbon atom can be attached or is attached to 4 other atoms. So if you look at the chemical structure of methane, it has one carbon atom, and the way you draw it is just carbon and hydrogen, and it's hooked to 4 hydrogens. So that's what a methane molecule looks like. These are atoms. The whole thing is a molecule. It's one carbon atom, 4 hydrogen atoms. It's a methane molecule. If you draw ethane, it has 2 carbons. The carbons are always hooked to each other. And in order to draw it, now you're not going to be expected to draw this, but this is just something to help you understand what we're talking about as far as how many carbon atoms. And in a second, we're going to talk about the sizes of these molecules and how their characteristics and their behavior are related to their molecular structure. Remember the example we talked about, the jar of marbles. The marbles were intended to represent individual molecules and to emphasize the point that chemical behavior is determined by the behavior of its individual molecules. And we're going to take a look at this atomic structure, mostly from the standpoint of understanding the relative sizes of the molecules, because that helps to understand how they behave as far as how temperature affects them. That's about as far as we're going to go in the chemistry part right now. So ethane has 2 atom molecules, 2 atoms of carbon. This is an ethane molecule, 2 atoms of carbon and that many hydrogens. Propane has 3 atoms of carbon, so the carbons are all hooked together, and then each one of those would be hooked to hydrogens. Each carbon is hooked to 4 things. When you look at butane, it shows 2 different kinds of butane. They have the same composition, but a different arrangement of molecules. Butane is represented by C4. It has 4 molecules. Of course, propane is represented by C3, ethane C2, and methane C1. Now, as your book explains, that's not the official chemical representation of these chemicals, but that's a common abbreviation in the oil field. Now, butane will be 4 carbons hooked together. There's 2 different ways that you can hook 4 carbons together. You can do them all in a row, or you can hook them together like that. So you can see these are all lined up. This has an arm going off of it. And then, of course, you hook all the hydrogens to that. The one that's all in a row is called normal butane. That's considered normal, just in a straight line. Normal butane. And then also can be abbreviated N butane. The one that has the arm or the branch going off of it is isobutane. So the straight line is normal. The one that branches is iso. You probably won't need to know the actual arrangements of the atoms to work in the field, but you may hear the terms N-butane, isobutane, and you just need to understand why you have those terms. They're the same chemical, they're just arranged differently, but they behave very similarly. Although if you look at it, there are some differences. When you look at comparing normal butane and isobutane, even though they have the same composition, their characteristics can vary. Their specific gravity is a little bit different when they're a liquid. Specific gravity when they're a gas is a little bit different, and their boiling points are significantly different. Vapor pressures are different. There are differences in them. You'll notice there's also isopentane and normal pentane, and it's the same kind of thing. Pentane is represented by C5, and normal pentane is just 5 carbon atoms all lined up together, and of course they would be attached to hydrogen atoms. Isopentane, just like the isobutane, isopentane has a branch going off of it. So what you need to know from that, you do not need to memorize. You're not required to memorize these structures. You do need to memorize methane has 1 carbon atom, ethane has 2, and you need to know what that means. That's 1 carbon atom. You need to learn how much, for each of these, how many carbon atoms do they have. And it's just a matter basically of memorizing. C1 stands for methane, C2 stands for ethane, etc. Now the other things we want to point out here, we're not going to look at all these numbers in detail right now, but we want to point out some of the characteristics that are important in allowing us to separate these things out. Remember, when the natural gas comes out of the ground, it's a mixture of these different chemicals. And depending on which well it's coming out of, you may have different amounts of these chemicals. But you almost always have all of these different chemicals in there. And ultimately, we want to separate them out. Methane is what is referred to as natural gas by people who are buying natural gas. It's the thing that's very commonly burned in homes. But when in the oil field, when you talk about natural gas, we're talking about all these things together. But ultimately, in natural gas processing, we're going to get the contaminants out and separate out each one of these individual components. And one of the main ways we can do that is by using their boiling point. By adjusting the temperature in a process vessel, we can cause some of them to boil and others to stay as a liquid. The ones that boil would be vapors. Those would be removed from that process vessel through a pipe at the top of the vessel where the vapors would exit. The ones that remain as a liquid can be removed out the bottom through basically a drain, or they can be removed through side pipes at different levels. But the fact that they boil at different temperatures and the fact that we have the ability to put them all in a process vessel and adjust the temperature to turn some of them into vapor and leave some of them liquid allows us to separate them out. It's pretty easy to separate a liquid from a vapor. The vapor's in the top of a vessel, the liquid's in the bottom of the vessel. Open the drain at the bottom, take the liquid out. You just separated the vapor from the liquid. So by adjusting the temperature of a process vessel, for example, if we put the temperature at 100 degrees Fahrenheit, that's right between hexane and pentane. If you're at 100 degrees Fahrenheit, everything above the normal pentane boils at a temperature lower than 100 degrees. So if you're at 100 degrees, that's going to be boiling. So everything above that is going to be a vapor. Everything below it is going to be a liquid. So if your process vessel is 100 degrees Fahrenheit and you let all the vapor out the top, you're going to have all of these things go out the top and all these things will go out the bottom. By adjusting your temperature, you determine which things are vapor and which things are liquid, and that's how you can separate them out. Now, another thing we want to point out here is the specific gravity of gas. You have specific gravity of liquid and specific gravity of gas. Specific gravity refers to a reference. It's comparing it to something else. And in both cases, it's comparing it to a common material. When you talk about liquid specific gravity, we're talking about the density of the liquid or the density of the gas. When it's liquid, we compare it to the density of water. And the specific gravity of water liquid is 1. When we're talking about gas specific gravity, we're comparing it to the density of air, which is also designated as 1. And the way you calculate these, you just, for example, for methane, you figure out the density of liquid methane and you divide it by the density of water. And so the specific gravity tells you the density of methane compared to the density of water. Same with air. Now that's for liquid, this is for gas. The specific gravity of methane gas is compared to the specific gravity of 1. So what this tells you is, since water is 1, anything that has a specific gravity less than 1 is lighter than water. It weighs less than water. So all of these are less than 1. So they are all lighter than water. Okay, when you look at the gas and you look at all of these, there's only one of them that's less than 1. Only one of them is lighter than air. Remember, liquids compared to water, gas is compared to air. Air is 1. Methane is 0.55. It's less than 1. It's lighter than air. All of the others, their specific gravity, which is their density compared to air, it's greater than 1. If it's greater than 1, it's heavier than air. So everything else, when it's a gas, is heavier than air. Ethane is pretty close to the density of air, but it's still a little bit heavier. So what's the significance of that? What happens if you get a gas leak in your gas processing plant, or even out at the well where you have natural gas? If you get a leak in some vessel and you get a gas escaping, if the gas that's escaping is lighter than air, it's going to float up into the atmosphere and go away. If it's heavier than air, it's going to sink in the air. It's going to fall down to the ground. It's going to be where you are. Gases with a specific gravity greater than 1 are heavier than air. If they're released into the air, they're going to sink. They're going to fall to the ground. They're going to be on the ground with you. And these gases are flammable.